Hello, good morning, good afternoon. I'm going to introduce you what is called the decoupled DC power flow. It is a linearization of the equation of the power flow that we have already seen. It is called DC but doesn't have any connection with direct current. It's probably a very bad name for this power flow, but think about this is just a linearization of the power flow. Basically, we want to find some approximation for these nonlinear equations. Well, the first thing that you can probably think about is some kind of Taylor approximation. But those Taylor approximation requires approximation around one specific point. This DC power flow doesn't require us to know any particular point. Let's start with the first simplification. So the first one is, well, we are not considering any kind of resistance and there is no shunt admittance. Now, any line will be modeled something like this. So it will be a series element. This series element is the reactant of the line. Let me recall what is the admittance matrix. It has two components, this real part and the imaginary part. Real part was related with the resistances. So we have only B, and Bij matrix will be 1 over these reactants. Okay, knowing that, so we can start to cross some terms. So for example, here in this branch flow, this is already crossed, this is crossed. We don't have this shunt admittance, so we don't have this element, and this part also is crossed. With that, we have these two expressions for the active and reactive branch power flow equations. They look more simple, but still they are not linear. We have cosines and we have sines. So just recall to what is delta ij is equal delta I minus delta j. So let's start to work with this expression of this power flow in the average power or active power. Another simplification for this DC approach is, well, let's consider that we have voltage very close to 1. And this can be in somehow assumed because voltage are transforming to per unit and they will be very close to 1. And the second approach will be, well, let's consider that this sign of delta ij, it's approximate to the first order approach of the Taylor series of this sign. So to remember, sign is something like this, and the first order approach is something like this. And this expression is fully linear. So we say like any power that go from I to j, it's approximately proportional to the difference of angle between I and j. So this actually is giving us a very good intuition if we have two nodes and we have some power flow. This is I, this is j. We have some power flow going from I to j. Could be positive or negative. So positive means power goes from I to j. So it will be very easy to see if direction of power goes in one direction or another. Just checking what is the difference of phase angles between these two nodes. We can do something similar to the reactive power. So reactive power, after crossing terms related with the resistance and shunt elements, we have this. So let's consider also first order approach of the cos of delta ij is approximately equal to 1. And voltage also we can consider approximately equal to 1, but not for all terms. Let's work with this. This qi is equal to bi minus bj divided by xij after crossing this term. Still, this is not linear because we have this multiplication of this vi with bi and this vi with this bj. So now here we are going to consider this linearization with this bi. So we cross this term and then we end up with this linear expression. Again, this is something very simple. This is linear and depends only on the difference voltages between two nodes. Now let's start to see how we can apply this. Let's assume that we have the same power system than before. We have a 3 nodes system, 3 lines. There is generator in node number 1, there's another generator in node number 2. We have knowledge about what is the production of the power of 2 and what is the demand in node number 3, active and reactive. So this bus is a PV bus because the voltage is fixed to given value. This one is a slack because we have voltage and phase angle fixed and given value. So if we want to solve this decoupled DC approach, we need first to assume like our lines have only reactance. Means like this resistance is not considering in here. So let's start to see how we can solve that. We're going to start with the active power. So we know like P1, this injection in node 1 in here, is equal to the power that go from 1 to 2, this power that go from 1 to 2, plus the power that go from 1 to 3, this power. Okay, but we have very nice expression for branch equation, power that going from 1 to 2. It was delta 1 minus delta 2 divided by reactance between 1 and 2. And then we have the power that go from 1 to 3 is delta 1 minus delta 3 divided by reactance of 1, 3. Well, in this case, delta 1 is always 0. And reactance for all the lines are 0.1. So I have minus delta 2 divided by 0.1 plus minus delta 3 divided by 0.1. This is minus delta 2 minus delta 3 divided by 0.1. Again, I will bring here P1. I don't know what is P1, so I keep like variables. I can write the same for the net injection power in node number 2. This is equal to power that go to 1, power that go from 2 to 3. And this is delta 2 minus delta 1, which is 0, so I'm not using this, divided by 0.1, because this is the reactance, plus delta 2 minus delta 3 divided by 0.1. This is equal to 2 delta 2 minus delta 3 divided by 0.1. In this case, I really know what is the injected power, which is 0.8. So this is 0.8. And I have another equation for 3. In this case, power that go from 3 to 1 plus power that go from 3 to 2. So you can imagine I'm writing the power that go from 2 to 3 and power that go from 3 to 2. They should have different sign. Well, in this case I have delta 3 minus 0 divided by 0.1 plus delta 3 minus delta 2 divided by 0.1. This is equal to 2 delta 3 minus delta 2 divided by 0.1. And I know what is this injection power. This is minus 0.8. Okay, so I know that now I have 3 equations, and I have 1, delta 2, delta 3, 2, and 3 variables. Here delta 2 and delta 3 appears again, and here also they appears again. So I have 3 linear equations with 3 variables, so this is very simple to solve. Obviously, this can be solved in a systematic way. So for here it's clear to have delta 3 is equal to 2 times delta 2 minus 0.08 that I'm going to use to replace in here and to get what is delta 2. So delta 2 replacing in this part will be equal to 0.08 divided by 3, and this is 1.52 degrees approximately. By using this delta 2 and delta 3 in here, so I can say like, well, delta 3 is equal to minus 0.08 divided by 3, which is equal to minus 1.52 degrees. And finally, if I'm replacing delta 2 and delta 3 on the top in here, you see this difference will be 0. These two guys will be 0. It means like, well, P1 is equal to 0. Well, now we have solution for this active power and phase angles. Here we don't need to use any information of the voltage magnitude or the reactive power. And another observation of this approach is power in 1 is equal to 0, and we can see what is generated in 2 is 0.8 and what is demanded in 3 is 0.8. So basically we don't have to produce anything with generator 1 because we don't have any resistive elements. Resistive elements are the responsible of the losses of active power in transmission grids. Let's do for the reactive power. We know that reactive power for I to J is equal Bi minus Bj divided by Xij, the reactance. So let's start writing equations. So for injection in 1, let me start with this one. So it will equal to the active power that go from 1 to 2 and active power that go from 1 to 3. When we work with the third one, we will have some reactive power going in this direction that we call 3 to 1. In 1, so we have Q12 plus Q13. And this is equal to B1 minus B2 divided by X12 plus B1 minus B3 divided by X12. What things do I know from here? I know B1 is 1, this is 1. Also I know B2 is 105. And also I know this guy, this is 0.1. So this will be equal to 2 minus 105 minus B3 divided by 0.1. This is equal to Q1. I'm writing again here. And that will be my first equation. I have similar definition for the node 2. So I have Q2 to 1 plus Q2 to 3. In this case I have B2, which is 105, minus B1, which is 1, divided by 0.1, plus B2, which is 105, minus B3, which I don't know. So this is a decision in my problem, divided by 0.1. So this is equal to 2 times 105 minus 1 minus B3 divided by 0.1, and this is equal to Q2, and in this case we don't know what is the injection in this node number 2. So I keep Q2 as a variable So this is another equation. And the last one, Q3 is equal to Q31 plus Q32. This is equal to B3, I don't know, minus B1, which is 1, divided by the reactance between these two lines, 1 and 3, plus B3 minus B2, which is 105, divided by 0.1. And this is equal to 2 times B3 minus 105 minus 1 divided by 0.1. This is equal to Q3, and in this case we know what is the injection in node 3. This is minus 0.6. So this is my third equation here. Well, you can see I have one variable, V3, two variables, Q1 and Q2, three variables. This is V3 again, this is V3 again. So I have three variables and three linear equations. So I can compute what are the values for each of those variables. In this case, B3 is equal to 0.995. Q2 is equal to 105. And Q1 is equal to minus 0.45. Okay, this is very close to 1, so as expected, Q2 is something positive and Q1 is negative. So it means that this slack bars, this generator, is absorbing some reactive power. Here I'm giving you a table with the final results. In the left you have this AC formulation of this alternative current of this original formulation. I will call HC just to make emphasis. This is the full formulation, so there is no approximation on that. Any solution of that will be solution of the power flow equations. For the voltage, we fix node number 1, node number 2, and node number 3 was calculated. If we compare from here to the DC approach on the right hand side, it is very close. Of course, not the same. So we can have very fast initial guess of what is going on in the system. And as you remember, so linear system of equation have very nice property if we check for the rank of the matrix which is forming this linear set of equations. This is why this linear approach makes very interesting approximation for the power flow problem. Going back to the active power in node 1, because in 2 and 3 is fixed. And while this is very close to this one, reactive power was fixed in node 3, but node 1 was computed. So there is a quite important difference here, and also not so much in the node 2. This DCPF actually can be used even for initialization of Newton-Raphson, because this is what you see here is a flat star for node 1, and this is fixed. But for node 2, so we can give this value. For node 3, we can give this value. And those values are very close to what we observe in the solution of the full formulation for the power flow. So we are expecting to have not so much iteration on the Newton-Raphson methods.